Hello everyone, so in this video we will be discussing logarithmic functions. So logarithmic functions is a function that takes the form f of x is equivalent to log of x with base b, where b must be greater than 0 and must not be equal to 1. So log x is an understood base of 10, while log of x with the base e is equivalent to ln x, or what we call the natural logarithm. So ln x is what we call the natural logarithm. So first we'll discuss the parts of our logarithmic function. So we have here log, or the logarithm, and we have the 8, which is what we call the argument. We have the subscript here. The subscripts are what we call the base, and the value after the equivalent sign is what we call the exponent. So that is what composed of our logarithmic function. Now let's move on to the exponential and logarithmic functions. Y is said to be equal to log of x with base b if and only if x is equivalent to b raised to y. So meaning to say, x now is equivalent to our base and our exponent. So this will be the form of our in exponential form. This is in logarithmic form, and this is our exponential form. So we have here an example expressed in exponential form. Number 1, we have log of 100 with base 10 that is equivalent to 2. Now again, 10 is our base, 100 is our argument, and 2 is our exponent. So transforming this one into the exponential form, so meaning to say we have our base, which is 10, our exponent, which is 2, that is equivalent to 100. Now if you try to check this one, 10 squared, that should be equal to 100. Now as we know, 10 squared is equivalent to 100, so meaning to say this is already correct. We already transformed our logarithmic form into exponential form. Now another example, we have the ln w, which is equivalent to y. So ln w, again, that is equivalent to ln of just to uh, review again, ln of x is equivalent to log of x with base e. So in this case, meaning to say, if our x is equivalent to w, meaning to say we can transform that one into equivalent of log of e, that is equivalent to w, is equivalent to y. Now base again is our argument now, so meaning to say we have e raised to y, and then this argument will be our equivalent. So meaning to say this is already our exponential form of this one. Now let's move on to another example, solving for the unknown. So from here, the example is log 27 of base b is equivalent to 3. So the unknown here is the variable b. We need to find the value of our b from the example. So that being said, we can transform that one into exponential form so that we can find the unknown in a simpler way. So we have b raised to 3, which is the exponent and equivalent to our argument. So in order for us to get the value of b, we can multiply by cube root both sides so that we can get the cube or the exponent there. So we can cube both sides, or cube root both sides. So that can be cancelled. So b now is equivalent to cube root of 27, and we know that the cube root of 27 is equivalent to 3. So meaning to say, the unknown variable or unknown value there is that b is equivalent to 3. So meaning to say this one can be replaced by b raised to 3. Now rechecking that one, if we'll plug in our base, which is 3, meaning to say that is log 3 of 27, that is equivalent to 3. Now if you recheck that one, 3 raised to 3 is must be equivalent to 27. Now if you calculate this one, 27 3 cubed is equivalent to 27, and that is equivalent to 27. So meaning to say we got the correct answer, which is this one. Now we'll move on to another example. We have log 25x is equivalent to negative 1 half. So the variable or the unknown value here is the value of x. So that being said, again, transforming this one into exponential form, we have 25 raised to negative 1 half. That is equivalent to x. So from that, we can easily calculate our value of x. So as we know, any number raised to negative 1 half, that is equivalent to the reciprocal of the square root of the number, which is like this one. And we know that square root of 25, that is equivalent to 5. So meaning to say we have 1 over 5 is equivalent to x. So the value of our x now is equivalent to 1 over 5. And then we have the discussion of the properties of logarithms. So before we proceed with the much complex problems with logarithms, we just have to keep ourselves we keep ourselves reviewed or knowledgeable with the properties of our logarithms. So if the first logarithm or the property of logarithm is here is we have the product of our functions, logarithmic functions, that can be separated into its addition. Meaning to say, log of AB with base B can be separated with log A base B plus log B base of B. And we also have the logarithm of our A over B can be separated with the log A with base B minus our log B with base B. So we also have the exponential form, or we have the log A raised to n, where n, or the exponent of our function or of our argument here, can be written before the logarithmic sign or logarithmic symbol. So it can be transformed like this. And we also have the log of nth root of our a, which can also be written as 1 over n, since as we know, this one, nth root, can also be written as a raised to 1 over n. And as we know, by the power or the exponent property, we can put this one before our logarithmic sign. So that gives us this one. And we also have the log b raised to x with base b, that is equivalent to x. Why? Because if we have the same value of our base and our argument, if they has the same value, we can just equate that one into one, so that will give us the only the value of x. And we also have the b raised to log of log x with base b, that is equivalent to x. So now let's proceed with some examples that can be applied, that must apply the properties of logarithms. So we have here a first example: express the following as a logarithm of a single expression. So meaning to say, as you can see here, this is composed of multiple expressions, this one as well. So we need to express those one by combining them so that we can come up with a single expression. So for using the properties that we've discussed just earlier, as we know, addition can be combined into multiplication. So meaning to say, for this one, um, this is the exponential law or the property. So meaning to say, we can put this as log 2x cubed plus log of 2, 3 squared, right? Afterwards, since they has the same logarithm and they has the same base, then we can just combine that one. So we have log of 2 multiplied by x cubed, log of x cubed multiplied by 3 cubed. I'm sorry, that's 3 squared. So afterwards, we can still simplify this. So we have log of, with base 2, we have 3 squared, that is equivalent to 9, x cubed So meaning to say this is already the combined or the single expression of this problem or this expression. And for the other example, we have here 2 ln x plus 5 ln of x minus 2 minus 2 ln of x plus 3. So you must not confuse yourselves. Ln and log is just basically that they has the same properties lang. So you can just apply the properties of the logarithm to our natural logarithm. So that being said, we have for this one, we can put that as ln of x squared. For this one, we can rewrite that one as ln of x minus 2 raised to 5. And for this one, we have ln of x plus 3 raised to 2. Again, numbers before the ln or the logarithmic sign or symbol or letter is understood to be the exponent of our argument. So that gives us this. Now, as we know, if they are separated with addition sign, they can be combined as multiplication. So we have ln of x squared, and we have the x minus 2 raised to the fifth. And then we have minus ln of x plus 3 squared. And if they are separated with a subtraction sign, they can be combined as equivalent to quotient, right? So meaning to say we have ln of x squared multiplied by x minus 2 raised to the fifth all over x plus 3 squared. Now, if you can still simplify this one, then you can simplify, but since the instruction is just to express our logarithmic expression into a single expression, then this is already fine. So this is now our final answer. So we have here another example, exponential and logarithmic equation. So we have to find the solution set of the following. So for this one, if the problem is asking you to find the solution set, meaning to say you need to find the value of your unknown, or you need to find the value of the unknown. So for this one, for number one, we have x plus 1 is equivalent to 2 with base 2. So again, you can just rewrite that one into exponential form. So we have the base and we have the exponent, which is 2, and that is equivalent to our argument, which is x plus 1. Now, so to get the or to isolate our x, we can just move our positive 1 to the other side of the equation. So that gives us 2 raised to 2 minus 1 is equivalent to x. So as we know, 2 raised to 2 or 2 squared, that is equivalent to 4 minus 1, that is equivalent to 3. So meaning to say our x has the value of 3. Meaning to say 3 now is the solution set of this problem. So now let's move on to our problem number 2. So for the problem number 2, this is already given as the exponential form. So now, in order for us to get the result of our x, then we can transform this one back to its logarithmic form. So again, this one is the base, meaning to say we have log 3. This is the exponent, so that is after the equal sign, and this is our argument. So meaning to say we have this one. Now if you try to calculate this one, that is equivalent to 4. So meaning to say x is equivalent to 4. So that's it. That is very easy. So if it's hard to find the answer in exponential form, you can try to transform that one into logarithmic form, and then you can check if you can find the answer. So now we have another example. We have here, I'm sorry, we have the last example here. We have number 3, which is 10 raised to 2x minus 1. So for this one, to solve this one, we can transform this one back again to its logarithmic form. So I mean to say this is again the base. So we have log 10, and we have the argument, which is 100. That is equivalent to our variable or our exponent, which is 2x minus 1. And as we know, if the base is equivalent to 10, you can also choose not to write that one. So we can just have that as log 100. And if you calculate log 100 from your calculator, that is equivalent to 2. So meaning to say log 100 is equivalent to 2, and that is equivalent to 2x minus 1. So to get the solution set of our x, we can move our constant to the other side of our equation. So we have 2 plus 1 that is equivalent to 2x. Now to isolate the value of x, we have to multiply both sides by our 2 so that we have 3 halves that is equivalent to our x. So meaning to say 3 halves now is the solution set of our equation or our problem. So another example is our 4. Number 4, we have 3 raised to 4x minus 2. That is equivalent to 5 raised to x minus 1. So the same rule or the same process. So we can have this one again transformed into logarithmic function or format. So again, this is our base, right? This is our base. This is our exponent, and this is our argument. So that being said, we need to transcribe this one or transform this one into logarithm. So we can have this one as log, and our base is 3. Our exponent is, or our argument is 5. We have 5x, 5 raised to x minus 1 is equivalent to our argument, which is 4x minus 2. So as you can see, we have two variables on both sides of our equation. We have a variable from the left side, and we also have the variable at the right side. So this one as exponential law, again, we can write that one as x minus 1. And then we have the log. We have log 3, and we have the 5. That is equivalent to 4x minus 2. Now afterwards, we can distribute this, the exponent, to our log 3, 5. So we can have x multiplied by log 3 or log 5 with base 3, and we have log of 3 and 5 that is equivalent to 4x minus 2. Now afterwards, we need to combine the terms which has the variables x. So as we know, this is already constant, so we'll need to move that to the other side of our equation. So we have x log of 5 with base 3 minus 4x, and then we have moving this log 5 base 3 to the other side, so we have positive log 3 5, and then we'll remain this one because this is constant, so we have log minus 2. So to isolate the value of our x, we need to factor this one. We need to factor our x since that is common with the two terms. So we have x log of 3 5 minus 4 is equivalent to log of 5 with base 3 minus 2. So divide that both sides by this one so that we can cancel this, and we can have our x remains on. We can isolate our x, so we can divide that both sides by log 5 of base 3 minus 4. So meaning to say, we can cancel this one now, and the value of our x now is equivalent to this one, log 3, 5 minus 2 all over log 5 with base 3 minus 4. Now, if you calculate that one, that is approximately equivalent to 0.211. So meaning to say, the solution set now of our x is equivalent to the approximated value of 0.211. So this is how we find the solution set of our logarithmic function. So those are all the discussion for this video, and I'll see you on the next video.